Hello, welcome, and thank you for joining the presentation A 40-meter telescope in your backyard, which is all about a new generation of very large telescopes, and they will be discussed from the perspective of an amateur astrophotographer. This presentation was originally held for the Astronomical Society of North Drenthe in the Netherlands in March 2020. The content of the presentation follows the following topics. We will first have a short historic perspective. Then we will look into the technological breakthroughs that have made these monster instruments possible. And then we will look at the 3 mega telescopes that are currently in development. We will have a look at some of the instruments, and we will look at the scientific purpose and the scientific goals that are being pursued. But let's first have a look at a bit of history. When we talk about mega telescopes from the past, I think one in particular needs mentioning, and that is the William Herschel telescope. It was built in 1789, and for 50 years this was the largest telescope with a diameter of 1.2 meters. It was also referred to as the 40-foot telescope, which was referring to the length of the tube. For many years, size of telescopes haven't really changed very much until last century, where we saw a gradual increase in the diameter of telescopes from around 1 meter in the 1900s until roughly 8, 9, 10 meters around the beginning of this century. So why is that? Why did the diameter of telescopes not increase beyond this point of, let's say, roughly 10 meters? There's a couple of different reasons for that. One is that if you have a mirror of 8 to 10 meters in diameter, it just gets physically too big. It's very difficult to carry these things up to the mountains that these telescopes are typically placed on. They're very challenging in maintenance. The mirror has to be taken out and into the telescope from time to time to be re-illuminized. It's just practically very difficult to handle. Second reason is that there is a resolution that is limited not so much by the optics but by the atmosphere. Resolution is a function of diameter of the mirror, but once you get beyond 1 to 2 meters, the resolution of the telescope way outperforms what is possible to see through the normal atmosphere. So these telescopes are not diffraction limited, as we call it. They're limited by the disturbances in the atmosphere. The alternative for that is to go into space, and that's what has been done. The Hubble telescope has given us enormous observations from space with no atmosphere whatsoever. So for many years, the size of telescopes did not change that much. But now we're in a turning point in history where we see telescopes being developed with mirrors that are significantly larger. This includes the giant Magellan telescope with a diameter of about 25 meters, the 30-meter telescope with a diameter of, the name implies it, 30 meters, and the European extremely large telescope with a diameter of almost 40 meters. A real turning point in history. A personal turning point in history was in 2017 when I bought my own telescope to be put in my own backyard. And throughout this presentation I will make reference to telescopes that are used by us amateur astrophotographers. In my case, that is a refractor with a diameter of 13 centimeters with a focal length of a meter, focal ratio 7.7, with a fairly standard astro camera, the ASI 1600, used by many in this hobby, and with a set of filters enabling us to do broadband and narrowband imaging. I think many amateur astrophotographers will recognize this type of equipment, and I will use this as a comparison throughout the presentation. Just to get another view on the size of these new instruments. These are many of the large telescopes that are currently in production or in development. And you can see with the blue arrows the 3 new ones that we're talking about, and they are massive. if you compare it to a tennis court or a basketball court, they're just absolutely gigantic, and also bigger than anything, and significantly bigger than anything we've seen so far. And big mirrors need big buildings, so also the buildings in which these telescopes are housed are industrial complexes, some nicer than others, but there are just gigantic buildings in which an astro backyard telescope is just more like a speck of dust than anything else. So what are the technological breakthroughs that have made these enormous telescopes possible? There is a total of 3, I think, which are the most important ones. First has to do with the segmentation of mirrors. The second is to do with active optics. And the third one is about adaptive optics. Let me explain each of these 3 areas. If you have a limitation on the size of an individual mirror, you can, of course, combine multiple mirrors to make a larger mirror, and that is the concept behind segmented mirrors. The largest mirror currently being produced is 8.4 meters, and anything bigger than that is pretty much impossible due to weight and handling restrictions. So if you want to combine multiple mirrors, you can do that in different ways. One more traditional way is what's called interferometry. You essentially combine mathematically the signal of multiple instruments. An alternative is that you build one telescope with one focal point, but you use multiple big mirrors, the biggest mirrors you can get, and you just combine a couple of those into a large telescope. That is what the approach has been in the Giant Magellan telescope. But if you put multiple mirrors into one telescope, you could also opt for much more smaller segments and have a bit more flexibility in the design of your telescope and make it all a little bit more able to handle. And that is what is currently the state of the art, I think, in modern telescopes. Each of these solutions, they have their own challenges. If you go into interferometry, it is technically very challenging. It does add resolution, it does not necessarily add sensitivity. And you're still dealing with very large mirrors. If you have multiple mirrors that share one joint focal point, the challenge is that each individual mirror needs to be asymmetrical, which is very difficult to polish. And you have to have a lot of them. But still, these multiple mirrors is currently the way to go. If you look at the James Webb Space Telescope, they have this design, and most of the new big telescopes, they have a design like this. So in the quest for making large telescopes and large mirrors, the largest mirror we currently can build is a mirror of 8.4 meters in diameter, and there is a special production facility in Arizona where they can make these type of mirrors. And here you see pictures of how that process goes. On the top left you see people putting down the individual blocks of special low expansion E6 glass. That is the base material for these mirrors. Then you see that actually this is in an oven. This glass will be melted in the oven. And in the bottom left you will see that during that melting process, the oven is actually turning. By turning the oven, you get a parabolic shape of your mirror, and that helps a lot in the polishing phase afterwards. If you already get a base shape in the glass, then you need to do less polishing afterwards than if you start with a flat mirror. The other advantage is that in this way you get what is called a meniscus mirror, so it has the same thickness throughout the surface, whereas in a regular flat mirror you have high thickness on the edges and low thickness in the middle. The total size, the maximum size of a mirror made this way is 8.4 meters in size. An alternative is to go with much smaller mirrors, and what is current state of the art is to use hexagonal mirrors of a size of 1.4 meters, much easier to make in high quantities. They have a thickness of only 5 centimeters, so much easier to handle. And you can combine them in a honeycomb pattern and basically accommodate any type of configuration that you like. One of the challenges with segmented mirrors that share one focal point is that each mirror is not parabolic, but is part of a larger parabol, and therefore you need to asymmetrically polish these mirrors. And the way that it's been done is that you start with a flat piece of glass, you apply pressure under that piece of glass with actuators in a shape that is computed as being the new shape of that segment of the mirror. Then you polish it flat, and then you release the load that you've applied, and then the mirror springs back into its original shape, and now you have a polished surface of that mirror which is exactly fitting for that segment in that location in the big mirror that is going to be applied in. This is called stressed mirror polishing. The second technology that really was a breakthrough for these large mega telescopes is called active optics. The idea is that when a diameter of a mirror gets bigger, the weight of the mirror itself becomes limiting. And you can go a long way with lighter glass and hollow constructions for support to help. But at the end of the day, that is insufficient to get to the sizes that we're talking about now. So in contrast, what is happening is that the mirrors are placed on a bed of actuators under the mirror that constantly help control the structure of the mirror. So on the bottom left, you can see that schematically drawn, a multiple array of actuators that constantly keep the shape of the mirror the way it's supposed to be. Also when the telescope is rotating and pointing up and down, which has a big effect on how the forces on the mirror are being applied. Constantly the shape of the mirror is adjusted by these actuators that are under the mirror. If you compare that to a passive optic system, as I would call it, in more of an amateur astrophotographer mirror, like for example a 10-inch Newton telescope, obviously this is a way different methodology. And the nice thing about active optics is that you can go to way thinner designs. If you take that 10-inch Newton mirror, that usually has a thickness on the higher end of about 3.5-4 centimeters high, which is a very thick piece of glass. If you extend that to 5 meters or 10 meters mirrors, you get into enormous thickness of mirrors. When you go to active optics, you're able to reduce that thickness of the mirror and thereby reducing the weight of the mirror gigantically. In comparison, for example, the giant Magellan telescope, if you bring that size of that telescope down to the 25 centimeters mirror of the Newton, you would get a mirror with only a 5 millimeter thickness, which is very thin. For the extremely large telescope, the effect is even bigger. There, if you would bring the extremely large telescope back to the size of a 25 centimeter Newton mirror, it would have a thickness of 0.3 millimeters, extremely thin. And you can also see here in this graph the difference between a regular mirror, as we know it, with a flat bottom and a curved top, to a meniscus mirror, which is the same thickness throughout the mirror, curved bottom and a curved top. The third technology that has been really instrumental in getting to the type of instruments that we see today is what we call adaptive optics. And I think this is the most impressive development I have ever seen in telescope development. What is it? Adaptive optics is a way to calculate the atmosphere out of the way. it's not new. It's technology that has been developed for military espionage, and that technology has been released at the end of the 80s. And different ways this technology has found its way into regular applications, and one of them is in astronomy. And the idea is that you put a flexible mirror somewhere in the optical path, and that with that flexible mirror you can correct for turbulence in the atmosphere. And ultimately you can enhance the resolution of your telescope to the diffraction limited theoretical resolution. Here is an animation of how adaptive optics works. If you do an observation and you have light coming in, that light will have a distorted wavefront because of slight disturbances in the atmosphere. And if you reflect that on a flat mirror, the distorted wavefront will be reflected and still remain distorted. But if you're able to correct the surface of your mirror in the opposite way as how your distorted wavefront comes in, it corrects your distorted wavefront and makes it into a straight wavefront. 3 things need to happen for that. One is you need to have a measurement of the atmospheric turbulence, including the local variations. Second, you need to do that very fast, and you need to be able to correct based on that very fast. And 3, you need to have a mirror that is flexible enough to apply the corrections necessary. So let's have a closer look at how this is solved in real life. Measuring the turbulence is done by measuring the twinkling of a reference star. Now the point is that you need a star of at least magnitude 9, because you have to analyze the signal very often. That means that your net exposure is less than 100th of a second, and therefore you need to have that amount of light to come in. Now many of these telescopes have a very small field of view, so often you will not see stars of magnitude 9 into the field of view. The solution there is to create these stars yourself, and that can be done by lasers that emit at a specific wavelength to excite sodium in the atmosphere at an altitude of 9 kilometers, and they create artificial stars. If you put multiple lasers around your telescope, you also get information on the variations across the surface. So the next thing you need to be able to do is to make very quick corrections. For that, there is an off-axis measurement of the signal, analyzed through what is called the Shack-Hartman lens array, and the signal from that is directly fed back into the actuators underlying the flexible mirror. So that is a feedback loop that is correcting the size and the shape of the mirror multiple times, 100 times or so per second. Finally, you need flexible mirrors, and not every mirror is suitable for that. You can't apply this to the whole 40-meter mirror that is in the big telescope. So typically this is done in one of the supporting mirrors in the optical chain. In the case of the ELT, this is a 2.4 meter, which is the 4th mirror in the optical chain. And that's a mirror of only 2 millimeters thick. And it's held by 8,000 actuators. These actuators, they connect to the mirror through magnets, and they respond within milliseconds to the signals that are coming from the corrections that are calculated based on the twinkling of the stars. Very impressive system. But more impressive even than the technology is the results that you get out of this. With this technique, which has been so refined now, you can get a resolution that is way higher than any of the space telescopes. For example, most of the telescopes here have resolutions that are up to 16 times the resolution of the Hubble Space Telescope. And you can see in the examples of the pictures what an enormous effect it has on resolution. And now, bigger mirror really means more resolution. So there is a point in going to 20, 30, 40 meter mirror diameter with using adaptive optics. Very impressive technique. So 3 megatelescopes are being built at the moment. Let's have a look at each of them. But before we do that, let's have one more view on how colossal these instruments are. This is enormous. The backyard observatory, as I mentioned before, is more like a speck of dust in the desert relative to what these enormous constructions are. The first one is the Giant Magellan Telescope, which is an overall diameter of 24.5 meters. It is built in Chile at the Las Campanas Observatory. There are other Magellan telescopes already in that same observatory, so this is the new one. It consists of a total of 7 mirrors of 8.4 meters each. That is that biggest mirror that can be produced. And the total diameter of the mirror is with that 24.5 meters. The resolution is 10 times more than Hubble. Cost is estimated around $1 billion, and first light is expected in 2029. I have to say, in all the estimates I have seen on either cost or timelines, pretty much none of the numbers is really holds for very long. So it's just estimates, and these numbers, they vary quite a bit over time. This is a picture of the webcam that you can find on their website. The construction site as of the 2nd of March in 2020. As you can see, there's still a lot to be done. Obviously, a lot of the work is being done on making the mirrors, which is happening as we speak. The second telescope is a 30-meter telescope, which is a telescope that will be placed in Hawaii in the Mauna Kea Observatory. That is a well-known observatory with many telescopes already there, and in total it's 30 telescopes, including the Subaru telescope of 8 meters and 2 Keck telescopes of 10 meters each. The arrival of the 30-meter telescope is not without dispute. The Mauna Kea mountain, the mountain tops are considered sacred by the local population, and therefore there has been quite a bit of resistance by the local inhabitants. But most of the concerns have been addressed, and it looks like building will take place on Mauna Kea. The telescope has a resolution of 12 times more than the Hubble telescope, and that is possible by its mirror that consists of 492 small segments of 1.4 meter each. Cost is estimated to be 1.4 billion, and the first light is expected to be in 2027. Again, numbers and timelines, take that with a grain of salt. This is a diagram of the internals of the dome, and this is just to illustrate what an enormous, complex telescope like this is. It is not just a telescope, it's a whole industrial enclosure where these telescopes are being built. The 30-meter telescope has a very specific design, quite unusual in terms of how the dome actually opens and positions itself. If you use the term eye in the sky, probably this telescope is closest from a visual point of view in that regard. And then the largest is the extremely large telescope. It's a telescope with a diameter of almost 40 meters. It is built in Chile in the Cerro Armazones Observatory, which is very close to the Las Campanas Observatory, so the other Giant Magellan Telescope, which has the benefit that a lot of the support facilities can be used between them. But they are in a different observatory in Chile. The mirror consists of 798 mirrors of 1.4 meter each, totaling a diameter of 39.3 meters. We already looked at the adaptive optics mirror for this particular telescope, which is 2.4 meters in diameter, 2 millimeters thickness, and 8,000 actuators to keep the shape of that mirror intact. This telescope has a resolution 60 times higher than the Hubble telescope. And also this one is more than $1 billion, 1.3 billion estimate, and the first light is supposed to be in 2025. The construction of the dome is a more conservative construction, a more common construction with sliding doors opening. And you can see the instrument here within that construction. A really massive building altogether. We also have a look inside of this telescope. You see here those yellow big tubes. They are the lasers that put the artificial stars in the sky. The other thing I think that strikes is that all these telescopes, they have a very compact design. If you compare the diameter versus the length of the optical tube, it's very compact. It's a very folded optical path with multiple mirrors in its pathway. All the telescopes have an LS mount, no German equatorial mount, so as we are used to in our amateur astrophotography. Obviously, mirrors and telescopes of this size would not be able to be put on a wedge or anything like that. The computers, they can correct the field rotation that is a consequence of this particular mounting. And here you see the lasers in action, producing the artificial stars and enabling the adaptive optics to do their work. This is the site in March 2020. As you can see also here, a lot of work still has to be done. It starts with flattening the top of the mountain, which is already a task in itself. Just to compare the telescopes in terms of specifications, so large diameters relative to an amateur telescope, also very large focal lengths, not so fast focal ratios, so you see focal ratios in the range of 8, 15, 17, so these are not particularly fast telescopes, but they are obviously extremely high resolution telescopes. Whereas in a regular telescope we're measuring resolution in arc seconds, for these massive telescopes the resolution is measured in milli-arc seconds. So if you read documentation about these telescopes, you come across the word MAS a lot, which stands for milli-arc second. So more than 1,000 different scale of resolution relative to what we're used to. The seeing, of course, in the areas that we're talking about here in Chile or in Hawaii is much better than in the typical backyard in Groningen in the Netherlands. So that is also helping to get the ultimate out of these instruments. Talking about instruments, what are the instruments that are attached to these telescopes? Often we talk about the mirrors and the size of these mirrors, but the actual science happens in the instruments that are behind them. And I say behind them, but that's actually not true. Whereas in our regular amateur telescopes, we typically put the camera and anything we want to measure at the back of the telescope. In the case of these mega telescopes, they usually have two platforms on the side of the telescope, and through the optical chain the light is being directed into individual instruments, and whilst one instrument is doing its measurements and another platform, other instruments can be prepared and being installed. These platforms are massive, comparing again to the backyard telescope, plenty of space for a whole star party on one of these platforms. So the instruments of these telescopes are very diverse. Here you see a couple of examples of instruments currently in development for the ELT. The the high resolution spectrograph, a mid-infrared ELT imager and spectrograph, a multi-object spectrograph, a lot of spectrographs really focusing on measuring specific elements in the stars that are being observed. Probably closest to what we would call a regular camera is the multi-AO imaging camera for deep observations, or the Mikado, which is a near-infrared imaging camera. The development of instruments like this is going on a continuous basis. So whilst the telescope, of course, is what a telescope is, constant new development of instruments is taking place with their own adaptive optics to further enhance the images that are being measured, with further increasing sensitivity and all those aspects. You see that managing this instrumentation is a high engineering job, although what is that engineering doing with this little ASI 1600, I don't really know. When we look at the imaging sensors being used, the real workhorse imaging sensor is what is called the Hawaii 4RG, H4RG. That's developed by a company called Teledyne, and Teledyne Imaging Sensors is producing this sensor in a 4000 by 4000 pixel array. So that's a 16 megapixel sensor, where the pixel size is either 10 or 15 micron. And they have sensitivity for visible light and near infrared. And the nice thing here is that you can combine multiple of these sensors into an array to make a much bigger surface altogether. These sensors are part of the TMT, the ELT, the Webb Space Telescope, etc. So these are really the workhorse sensors of modern astronomy. Just to give you a sense of size for these sensors relative to what we're used to, on the top left you see the ASI 1600, also 16 megapixel. But in the Giant Magellan Telescope, the 16 megapixel 15 micron sensor is applied. And in other sensors, in other telescopes, you see arrays of 4x4, so 16 of these sensors, creating a total of 256 megapixel pictures with a pixel size of 10 micron. I mean, this is just beyond anything we amateur astronomers can ever dream of. If you look at the specifications of the various cameras, you also see, of course, the big difference. Not so much in resolution. Giant Magellan Telescope has also 60 megapixel resolution, bigger pixel size. But obviously, because of a completely different focal length, you have a completely different pixel scale. So also your pixel scale is described in milli-arc seconds. Whereas for a regular telescope in the amateur astrophotography, you would probably be looking at a pixel scale of something like 1 or maybe 2 arc seconds. These telescopes, they have pixel scales of 0.00 something, 0.003, 4, 5 arc seconds, so 3, 4 or 5 milli-arc seconds. Enormous. The enormous pixel size of 10 and 15 micron obviously results in extremely high sensitivity and the ability to collect for long exposures a lot of photons. Putting it all together means that the field of view is extremely small for these cameras and these in combination with these telescopes. And to illustrate that, I've taken one of the pictures that I've made with my telescope and my camera, and indicated here is the field of view of the Giant Magellan Telescope with its 16 megapixel sensor, as well as the extremely large telescope with its 256 megapixel. So for reference, the big picture you see on screen is 16 megapixel, and the white box on the top right is in itself 256 megapixel. It's just insane how much resolution, how much detail those pictures will provide. Finally, some of the scientific goals that are underlying all these initiatives. And whilst there are differences between telescopes, overall the scientific goals are pretty comparable. And they are as follows. One, of course, is to look deeper into the universe, towards the younger universe. There's a lot of interest in black holes and dark matter and the laws of physics. There is a particular type of impossible stars called the brown dwarfs, of which we know very little, to which we hope these telescopes will give some answers. There's a lot of activity going on in finding and characterizing exoplanets, so planets that are present with other stars. And with all the spectrographs available, it is possible to measure the atmospheres of these planets to give us a better understanding of possible Earth-like systems in other stars. There's a lot of interest in the chemical processes following galactic collapses. For example, colliding neutron stars, exploding supernovae, etc. So really focusing on what is happening on a chemical level. And obviously, a lot of the research is also into understanding what the origin of life is. And I think the pretty much the most important one maybe is the unexpected. We don't know what we don't know. So we don't, with instruments that give this level of extra detail, which are able to look this much further into the universe, maybe we'll just see things we've never seen before. Maybe we will see things we've never thought of before. So the serendipity and the openness to see new breakthrough discoveries is extremely exciting. With that, we have reached the end of this presentation. I'd like to thank you very much for watching this video. You can find more of my astrophotography activities on the website astroworldcreations.com, on which I publish on a regular basis new images and new blog posts.